And welcome to today's edition of the Radiation Heat Transfer Learning Journal. So in the last video, we were talking about another expression or another form of DIDS, as well as the simplified version of the radiation transport equation or radiation transfer equation. So now we want to talk about solving the RTE, the radiation transfer equation, and we have this to start with. Now I said before that this transport equation was not particularly useful because it kind of hides a lot of detail. If you want to solve, let's say, if you want to solve, let's say, for the real numerical value of the heat being transferred. Okay. However, this equation still has some utility, some use, because what it does is that it tells us the physical meaning of what we are discussing. Okay, so let me explain what I'm talking about here. So I lambda. So remember we were doing some sort of first order looking differential equation, and actually S hat, yes. So we have an equation like this, and the way we solve it was, using this kind of a thing, the first order ODE kind of a thing, and we have something like this. And to use this equation 10.28 in Michael F. Modes's book to solve the RTE, it is not really practical because it's very hard to kind of get numbers from it, because there are so many ways this source term can vary. However, this equation still offers us some kind of insight as to what is going on. So I'm just going to copy this down. Hopefully you know where this comes from. This comes from, like, multiplying both sides by integrating factor. So d by d tau lambda, if I were to do it a similar way. What I mean is that we multiply both sides by integrating factor, and I use lambda instead of eta. Yeah, lambda being the wavelength and eta being the wave number. Okay, so I'm just going to copy this over, and I'm going to copy the exponential over. So remember what we are talking about here. This is the intensity, this is the integrating factor, which is the exponential of tau lambda. This is the source term, which, again, remember, it is the in-scattering term and the emission term combined together, and this is again the integrating factor. Now, like I said, this, if you want to get solid numbers out of this, not useful. However, this can help show us physically what is going on with the radiation transport equation. Because when you try and actually solve the equation, you can get pretty messy expressions. So for example, let's go and show you what chapter 14 is like. Okay, chapter 14 is chapter 14 is basically oh dear, let me collapse this. Okay, yeah, so chapter 14 is this. It is what do you call it? A general formulation for a plane parallel medium. So this is one of the first analytical solutions we are looking at. Now you can see pretty quickly it's going to get pretty complicated with many symbols and what have you. Sometimes dealing with so much algebra, it is very take a look. This is what the solution looks like. 1418. You see, you have I minus, I2, all these funny symbols, and it can get really difficult to catch on to what is going on. It can get really difficult to catch on to what's going on physically, especially yeah, when you have so much of these symbols to consider. Take a look at how complicated these equations are. Take a look at how complicated these equations are, and you try to imagine what is going on in the medium physically. It can get very hard the more symbols you are introducing yourself to. So the advantage of this little this equation 10.28 here, it helps us to see at least in a very simple mathematical manner what is going on. So I'm just going to write that down. I'm just going to write down 10.28 in the form of using lambda instead of eta. So what this basically does is just integrate both sides from 0 to tau lambda. Okay? So you integrate both sides. So on the right side, you integrate this from tau lambda equals 0 to tau lambda equals to tau lambda. Alright. So let me introduce the intermediate step here. So let's do the integration. Okay. Okay, so the right hand side, it is this. Integrate the whatever, whatever this term is. So from evaluated at, okay, so okay, let me do the integration proper first. So I'm just going to have this here and d tau lambda. So the right hand side is this variable here, right? Tau lambda. So I want an expression for going from tau lambda equals to 0, and it goes from there to tau lambda equals tau lambda. Now this again is a very improper way of writing this integral, but we can make do with that for now. I will try and do something more formal mathematically later on. So what are the limits on the right hand side? Okay, so the limits on the right hand side are as follows. Okay, so you're integrating this from I blah blah blah. This is evaluated at tau lambda equals 0. Alright, so I evaluate whatever this quantity is, this whole quantity at tau lambda equals to 0, and I evaluate it till tau lambda equals to tau lambda, right? So tau lambda equals to tau lambda. So that's all I'm doing here, and then I will want to have this little bugger here. So yeah, so this is what is going on. Okay, all right, so yeah, moving on. What can we do? Okay, so the integral is evaluated as such. Okay, so we will have, okay, on the left hand side is pretty straightforward. You're going to end up with this integral turning into this. So evaluate this at tau lambda equals to tau lambda minus whatever this is, tau lambda equals to 0. Okay. Alright, so yeah. What are we doing here exactly? So let's use a pint to illustrate what's going on once I finish integrating this. So on the left, on the right hand side, right? On the right hand side, it will just be left as such, because over here you can see there's just this integral. Okay, so let's evaluate this on the left hand side first. So this is evaluated, tau lambda. This is dependent on tau lambda. Now what is this expression evaluated at tau lambda? It is just, okay, wherever you see tau lambda, you replace it by tau lambda, right? So this expression will just be itself when it's evaluated. Okay, now what about this? This one evaluates at tau lambda equals to 0. So I'm just going to put tau lambda equals to 0 here. And this tau lambda here is to be replaced by 0, which is ultimately e to the power 0. And e to the power 0, as we all know, is just simply equals to 1. Okay, so I'm just going to replace all of this with here. Control Shift V and yeah. Okay, so once we can do that, we can just shift this over. And divide both sides by e to the tau lambda. So dividing both sides, we will just get this. We have a e negative tau lambda on the right hand side. And again, I think there's a proper way of writing this expression. So we cannot have, d tau lambda at, the both sides. I mean, we have to differentiate this tau lambda over here from this tau lambda here. So we are going to use the dummy variable, and over here they use tau lambda prime, or you can use tau lambda star, but we will just follow the convention. The proper dummy variable is tau lambda prime, so we will need to differentiate the one we are integrating, which we will call tau lambda prime, from this actual limit, which is tau lambda. Okay, so now we have done that. So this is wherever tau lambda is, right? And this will be a constant. Okay, so tau lambda is a constant. It depends on what we set tau lambda as, and we can actually bring, and since tau lambda is a constant, we can bring it in. Okay, we can bring it in, and all that does is to introduce this negative equation here. So minus, that will give you a plus. Minus gives you a plus. Then we can just bring this in. And I'll take this e to the minus tau lambda out. So all that said and done, what does this equation actually mean? Now let's bring up MS Paint. I'm going to color the background black for easier reference. Get this blue. Control O and delete. Okay. So, okay, I don't need to save anything here. Okay, maybe I'll just save heat transfer radiation. Okay, that will be my saving file. Alright, so what this equation is saying is that the intensity at some point, tau lambda, so let's say there's a certain optical thickness tau lambda. So I'm going to draw a line here. Okay. From This is the optical thickness being 0. So again here, I use tau lambda prime to indicate the variable optical thickness. And over here, I'll just use tau lambda prime equals tau lambda. And when I say tau lambda here, I'm referring to the optical thickness, the actual optical thickness of this whole thing, right? This is tau lambda. So the variable I use to describe whatever length along this whole line, I use tau lambda prime. When I want to refer to the length of this entire thing, I'll just use tau lambda. So that is the difference between tau lambda prime and tau lambda in this equation here. Tau lambda is this whole length, specifically this whole optical thickness. Tau lambda prime is, like the x-axis, x equals to 0, x equals to some value c, and this is something like x equals to 0, right? So that's all. Instead of using x, we use tau lambda prime to denote this variable. Okay. So let's say we have we want to find the intensity here, right? Intensity at tau lambda prime. That's what we are doing. So, or in other words, we can use intensity at tau lambda. So intensity at tau lambda is intensity at tau lambda prime equals tau lambda, right? So, and here is the intensity at tau lambda prime equals to 0. Okay, so this is what the equation is trying to find out. The intensity at this particular point, the radiation intensity, right? Radiation intensity at this particular point. Okay, so what is that equals to? Let's take a look at the equation. So first thing first, pretty simple. It refers to the initial intensity at tau lambda prime. Okay, so I'm just not going to mix up here. So lambda prime. So in order to make a consistent use of the same nomenclature, I'm going to put it as such. So we first look at this intensity. Of course, we start from the intensity here, and we know that let's say we have some beginning intensity here. We know that as we travel through some optical medium, it's going to attenuate, right? It's going to attenuate according to the optical thickness. So that's what you see here in this first term. So there's some initial intensity, and it's going to attenuate according to the optical thickness here, tau lambda, because this initial radiation is going to travel through all this distance and get weakened by scattering or absorption or what have you. So there's going to be some attenuation or some extinction, right, of this initial radiation. Okay. However, we also need to consider the contribution of the source. We also need to consider the contribution of the source term, right? So what are the sources here? Remember, there's the in-scattering plus the emission. Collectively, they can be represented by this source term here. And that is all along this whole stretch. So in the medium, there will be in-scattering. Let's say we can consider this point. There'll be an in-scattering source term, which we have to account for, as well as the emission. However, it is only traveling through this length, right? It's only traveling through this length. And what is this length? Well, this length is actually tau lambda minus, well, what is this length here? Tau lambda prime. So tau lambda is this whole length from start to finish, and there's this little bit of length that it is not traveling through. We call this tau lambda prime. Yep. So it is being attenuated by this length, tau lambda minus tau lambda prime. So that is just one source only. We have to consider that throughout this whole the way the radiation travels, there will be other sources here. I mean, you can imagine the whole way through, there are small little sources that are being attenuated as it travels through, and you have to sum them all up. So, for example, you have the initial source here, then you'll go through attenuation, right? There's this initial source. Maybe I'll use the yellow color. There's this initial source. Then, as you go through the medium, you have some other radiation sources as well. The inscattering and the inscattering and the what? Emission term, right? So this is going through tau lambda. Okay, so you along the way, there will be different source terms, all traveling towards the end. So this is along the same line here. I'm just drawing it in different like directions. And as you can see, the closer the source is to the finish line, so to speak, the shorter the optical distance the radiation has to travel through. So what is the final intensity here at tau lambda prime equals to tau lambda. So for this we just have to add all the contributions of this up, right? We have to add the contributions of this up. So the first contribution is this one. This one's the initial source, the initial radiation, which we have accounted for using this term. However, there are also the contribution of the emission and inscattering in the medium. So there will be a bit of emission, the source emission and scattering here, there will be a bit of emission and scattering here, a bit of emission and scattering here, and you go all the way through this whole line. So basically, the whole line can be so-called dotted with a lot of sources, and you got to add up the contribution of each of these sources, and when you sum them all up, so when you sum this all up, it is basically the integral that you see here. So what this is saying is that, okay, I have many of these different sources, and it's being attenuated by the length tau lambda minus tau lambda prime, as I was saying earlier here. This length is what is being attenuated through. And what basically happens is that I have to sum them all up. Okay? And that will give you the final intensity you see here. Right? So the intensity you see here, at the end of the day, it is basically just the contribution of the initial plus the contribution of the source terms. That means the inscattering and the emission as you go through the medium. And it's all being attenuated through the respective optical distances. For the initial source is tau lambda. For the radiation for each of the medium, here it is tau lambda. Of course, you subtract away how far it is from the beginning, which is this tau lambda prime. Hopefully that explains, that gives an intuitive feel of what this equation is trying to say. And of course, if you think hard enough, of course, let's say you have this. Let's say you have tau lambda prime equals to tau lambda, right? let's say you have some incident radiation impinging on surface dA. Tau lambda prime equals to tau lambda. Okay, well, you're thinking of it, okay, sure, there is some radiation coming on this surface here, right, from a particular angle theta. However, what about this radiation here? Is it the same thing? So I'll call it tau lambda 2 because it's probably a different length coming in. And they are not actually the same thing. So depending on the angle with respect to the normal, this intensity term will change. Why? Because I'm not just describing what the radiation from one angle. This equation over here, it doesn't describe the intensity from all angles. It's just describing the intensity at one particular angle, right? So if you can picture this like so, you will have some okay, let's say you have a long plate here, or you have some arbitrary surface, and then this is the area dA, and this is A1. You have some boundary there, and you have some medium here with a specific temperature, so there is some scattering and there is some emission. So from, let's say, at the normal, right? So this is theta equals 90 degrees. So along here, you will have some radiation at the beginning because this A1 may be emitting some radiation. Okay. And then as the thing travels along the medium, you have to sum up the contribution of each of the source terms along the line. So that's what the integral is talking about. And you go all the way, you sum up everything. So this is the integral. This is the integral. And this is the initial. Okay, this is the integral. Right, and this is the initial. So this is the initial, this is the integral, right? So it only tells you what the radiation from this direction is. Okay? If you're coming from, let's say, another angle, then you will have a slightly different, you have the same equation, but a slightly different integral. So over here, I'll use a different colored paint. So you have a different initial value of radiation, and then you also have to sum up the contributions from start to finish. And this is the integral you have to evaluate. So what this equation here is telling you is that for a specific angle, for a specific solid, little bit of the solid angle, you will have to consider the intensity at the beginning, which is this initial ones, plus the integral of the source term. So that accounts for the contribution of the source terms, right? So depending on what the angle is, you'll have to do this equation, again and again. So this thing does not describe the intensity for the whole, for every degrees. For the whole, it does not describe the intensity after you sum everything up across all solid angles. It just describes it at one particular, so-called pencil of rays. So remember what intensity was, right? Intensity, okay, equals to power per unit area or normal area per unit solid angle. So what is, you only have to, for this, let's say intensity here, this first one, maybe the solid angle is being bounded by these two lines here. It's a very small solid angle. So it's almost this straight line. So that's the intensity when you look in this particular direction. It will be determined by this orange line here. Now likewise, when you look from a different angle, so you consider the intensity depending on this solid angle as bounded by the second set of blue lines I've been drawing. So that will be determined by this orange line here. You do your initial and your integration. That's what you are actually calculating. It is not the intensity like power per unit area, or it is not the intensity that it is being received by the plate in total. It just tells you, if I look at this particular direction, the power per unit normal area per unit solid angle is based on this equation, right? So that really depends on the angle that you're going for. Okay, hopefully that helps you get some intuition as to what we are actually calculating when you see all these complicated symbols, right? At least when there's a picture, it's easier to describe what's going on. Okay, so yeah, so in the next video I'll probably want to go through some simple cases to help start the ball rolling on analytical solutions. So thanks for watching. I'll see you guys next time. Bye bye.